All right, good morning. Any questions? Any comments? So I want to start talking about a little bit more technical aspects of this course. So today I'll introduce bosonic quantum fields. Just like coherent states for like laser, but we are now going to do it for like bosonic atoms. So what we introduced last time was something like this. So we had some creation operator, AK. So this is acting on so-called occupation basis. Like let me call it N1 and 2 ... This guy goes and finds this NK ... and it just does what A and A daggers do. It's like this is take NK and increase it like this, and this one is exactly like, so this piece is +1 ... So this is exactly like single particle harmonic oscillator, but there are like these additional slots for additional A's and A daggers, and the other one is acting also similarly. So this one is, this is K, you go, you do this, and you decrease this one by 1. So these things, these are called occupation basis. And this representation is sometimes called Fock space. So this is Fock space. And this N1NK, this ket is defined by, okay, you take this and you do exactly like harmonic oscillator, but for like many slots. Like there's like A1 creation. How many do I have? N1. So I am going to put N1, and I am going to divide it by N1 factorial. And I'll repeat this for all the others. There's N2, ... and K. So this is N2, this is A2, N2, ... This is K, this is NK, and this is K, and ... This entire series of operators are acting on vacuum. So this is, if you want many particle vacuum, there's like no particle, basically empty space, and we call it vacuum. And the reason we like this representation better than like so-called first quantized usual Schrödinger equation is that you can carry all the calculations to operator commutations, and the commutations of operators is like AK dagger K prime is equal to delta K prime, and all the others are 0. If you have things like, for example, dagger, or if you have things like no dagger, this is 0. That's why these are like, you can see two operators here, like this one, you can think about this A K dagger, A K prime dagger acting on vacuum is same because of this commutation relation. With rather than creating K prime first, I can create K and later K prime, and this is kind of like a bosonic exchange. That's why we call this bosonic quantum fields. And this is all we need to know to do the calculations. We just keep track of commutations. These are what we call canonical commutation relations, and calculation just does it for us. And any operator in Fock space, or let me call it Hilbert space, can be written using A's and A daggers. I also want to define, okay, so these K's and K primes are general quantum numbers, but you can also think about them like momentum. If it is momentum, we can also define a real space version of this. Typically, what would make sense is like define something like A of R and A of R dagger, right? To introduce these A's and A daggers in the real space. But the convention is not this. People use psi. And this is creating a lot of confusion, but we have to be aware. So these are exactly like A's and A daggers. And this is introduced by Fourier transform of momentum space operator. So this is K e to the I K dot R. And this is, let me put heads, A. This is a vector. Now, if you are in 3D, this is like 3 components, and for each point in K space, I have a different A or A dagger. And similarly, I can define psi dagger. So this is psi dagger. So this is going to be minus, and this is going to be dagger. Now, by using this, you can immediately calculate this. If you put psi of R, and you put here psi dagger of R prime, there are like these momentum sums, K and K prime if you want, and there's like AK dagger prime, and if you, there's going to be like a delta function. If you carry out the calculation, this is going to be delta of R minus R prime. Does anybody want me to show this? This is pretty straightforward, but if you feel uneasy, I can do that. So this is exactly like this commutation relation, but in the real space, and all the others are again 0. If you have things like psi, or if you have things like psi dagger, they are all 0. And inverse transforms, you can also write inverse transforms. So A K is equal to 1 over root V. This is the Fourier convention utilized in the book. So this is going to be, actually let me write it like this. D cube R e to the minus I K dot R psi of R. And the other one is just the Hermitian conjugate. This is dagger, this is plus, and this is dagger. Now let's try to do what I advertised. We can write any single particle or many particle operator can be written in terms of A's and A daggers, or psi's and psi daggers. For example, I can start with number operator, and let's keep the index V. I can write these, as you can see, I can write this in K space, I can write this in R space, or if both K and R are not good, I can write them in any other basis I like. Right? I can find the good basis for my problem, and let's let this good basis be alpha. Number operator in alpha basis is going to be something like this, and alpha is A alpha dagger, A alpha. And these are operators, but I will forget. I think you'll also forget to write head at some point. In momentum space, for example, this is going to be nk vector is going to be a k vector dagger ak. So this is number of bosons at state alpha. This is the operator that gives us this object. And I can also define total number operator. So this is total number is n. I just sum over all states. I alpha and alpha, and this is, let me write it, alpha A alpha Dagger A alpha. So I can calculate kinetic energy. Kinetic energy. Let me use T hat for that. What is kinetic energy? I have minus h bar p squared over 2m, right? H bar squared over 2m del squared. And this thing should act, right? This is in real space, then I should choose the real space creation operator or creation and annihilation operators, psi. And if I do also this psi dagger of r, so this is the kinetic energy at point r, and if I integrate over all space, I have the total kinetic energy. Right? If any problems, we can slow down.
Is some kind of a unitary transformation?
So this one? So which one? This one? Or here?
B hits the momentum operator with psi and psi dagger from both sides.
So this one?
Yes, I didn't understand the logic behind.
So yes, I think you are right. You can also think about this in momentum space. Let's write it in momentum space, k. And in momentum space, what is the kinetic energy? It is h bar squared, k squared over 2m. And I need to count how many bosons I have at that k. And this is given by ak dagger ak. Okay, these are vectors. Now you can, if this is more familiar to you, now you can transform back to real space, and in the real space this is going to be the result. But for me, typically people start from here and go there, but I think it doesn't matter, whichever makes more sense for you. So this is the kinetic energy. If you have external potential, we can also write that. So I will use the letter U hat for that. And I'll use exactly the same logic. I have this thing, but rather than this kinetic energy operator, I need to have this U of R. And if you transform to like Fourier space, this is going to be now, because right there is like a UR dependence here. When you do the Fourier transform, right, there will be UQ, and this UQ is going to couple different K's. Like, let me write the result. So this is going to be K prime. This is U of K minus K prime. This is A dagger of K prime A of K. So like pictorially, if you start like introducing the Feynman diagrams, this is going to be something like this. So this is my potential, and my particle comes in. So this is the point R, and it scatters, right? So this is psi is annihilated at R, and psi is created at R, and this is U of R. Good. Or I can also think about the, okay, so this is the real space picture. I can also think about this in the momentum space. In the momentum space, I send something with K, and I receive something with K prime, and this becomes U K prime minus K. And now I don't have R here, okay? Good. The first time seeing this is a little bit weird, but you need to get a little bit used to. I think it's pretty standard calculation, but it is different from what we are used to in the first quantized conventional quantum mechanics. Let me introduce two-body interactions. Let's consider so-called two-body interactions. And for that, I want to use this abstract alpha basis, and then I will generalize. So in the alpha basis, suppose I have alpha particles in and alpha particles in alpha state and beta particles in beta state, and their interaction is given by some matrix element V alpha beta and alpha and beta, right? This is like density kind of interaction, and alpha is given by A alpha dagger A alpha, and their commutation is again A alpha A beta dagger is delta alpha beta. But here I have to be careful, right? So this alpha and beta can be the same or different. So let's consider these cases separately. Case 1, if alpha is not equal to beta, there is nothing to be concerned, right? This is exactly what I wrote. But case 2, if alpha is equal to beta, what I need to do is like I have this V alpha alpha, I can have n alpha particles interacting with the remaining particles, and the remaining particles are n alpha minus 1, right? Because if it was n alpha, here there would be like an interaction, particles interacting with itself, and that wouldn't make sense. And I can combine these two cases like this, so I can write this like V alpha beta n alpha and beta minus, if they are the same, I subtract 1, n alpha beta times n alpha, right? So now this incorporates both case 1 and this is case 2. And now I want to open this up. This is equal to V alpha beta. So this is A dagger alpha, A alpha, A beta dagger A beta minus delta alpha beta A dagger alpha A beta. And it is preferable to write this entire thing in such a way that A daggers are on the left, A's are on the right? Because we are going to act on the coherent state with this thing, and the coherent state likes all the A's on the right, all the A daggers on the left, because coherent state is like a eigenstate, right? Eigenstate of A's and A daggers. So that's how we did it at least last week in the single particle picture. To do that, I am going to just use commutation relation, this guy, this one here, and I'll write this as delta alpha beta plus alpha A beta dagger A alpha. And so you can see this term plus, right, alpha beta A alpha dagger A beta is going to cancel this term, and what remains is V alpha beta. Now I have this so-called normal order, A dagger, A, and these are all operators. And this is, I sorted like alpha, beta, beta, alpha. You can see there's also alpha, so maybe I can write it in 2 steps. So in the intermediate step, I have alpha, beta, A alpha dagger, A beta dagger, A alpha, A beta. But as I have showed above, this A alpha and A beta, they commute, so I like to write it in this form. So for the moment we prove this for bosons, but we can do exactly the same thing for fermions. Fermions also like being in this normal form, and index convention is exactly like this, alpha beta, beta alpha. Okay? So this is what we call normal order. Normal means all A daggers are on the left, all A's are on the right. So in the position basis, let's now come back from abstract notation to position basis. Position basis, I have a boson at R, another boson at R prime, and their distance they have like some, I don't know, something like Coulomb or some kind of two-body interaction that's only depends on r minus r prime. And the convention is I have this psi dagger, psi dagger, psi, psi, and this is going to be r, r prime, r prime, r, right? So these are all operators. And pictorially, we can think about this. I have a point r, another point r prime, and I have something coming in from r, something coming in from r prime. So these are psi and psi operators, right? These two, and then they scatter. So this is psi dagger and psi dagger. And using this, I can introduce total interaction. Let me use V for this total interaction operator. So this is going to be exactly like that. So this is, I need to integrate over d cube r prime. But to prevent double counting, I also need to put this 1/2. Good. Maybe I can spend just like a few minutes to transform this thing to momentum space to see how the labels play around. So this thing, let's transform to momentum space, is going to be equal to first these guys are going to be as they are. So this V of r, I want to write it in the momentum space like this. So let me write it Q V of Q e to d, what did I use? Minus I Q dot r minus r prime. So this is this one. Now I want to also write momentum of these. Let me write all of them at once. So this is going to be K1, K2, K3, and K4. And what I'm going to have is like a dagger K1, a dagger K2, okay, this is dagger, a K3, and a K4 times the exponentials, and I will combine the exponentials like this. This is e to d. Okay, K4 comes e to the I, K4 comes with r, and I have here K1, K4 minus K1 dot r, and e to the I have similarly K3 minus K2, K3 minus K2 dot r. Does it make sense? A lot of things, but the calculation is really straightforward. Now you can see I have...
Isn't the second exponential is r prime?
Oh, yes, thank you, absolutely. So this is r prime.
Also, we need to divide the whole.
Yes, and this is 1 over root, okay, each one comes with 1 over root 1. I think this is going to be 1 over v squared, right? Yes, thank you, absolutely. And I will use the delta function. And the delta function is going to be like this, right? Let me pick at least one to show you. So, for example, I can combine this object and this object, e to the I, qr, and this object, right? These three combined are going to give me, let me write what they are and then see. So this is d cube r e to the I k4 minus k1 minus q dot r, and this is going to be root v delta of k4 minus k1 minus q. And these are vectors, but we need to keep that in mind. And similarly, another root v is going to come from r prime integration, and at the end, what we are, and you can see now k4 is determined by this k1 minus q. What I can do is, let me write it like this. Okay, let me write and explain. So this is going to be 1 over 2v sum over all. So at the end, at the moment, I have 1, 2, 3, 4, 5 momenta, but 2 of them will go and 3 will remain. And these 3 I'll use k prime and q. V is going to come with a q definitely, and I am going to have a. So this is dagger. So let me put k and k prime, then this is going to be k prime plus q, this is going to be k prime minus q. Good. Or if you like the other way, you can also do it this way, it doesn't matter, because there's like a summation over q, and typically v of q is equal to v of minus q. Think about Coulomb, so things make sense either way. Good. So let me sum up. So our main object is going to be this second quantized Hamiltonian h. We can either write it in the real space or the momentum space. Let's write them. D cube r. So this is psi dagger of r. There's like so-called single body terms minus h bar squared over 2m nabla squared plus u of r psi of r. So this looks awfully like usual quantum mechanics, but we know it is not, right? It looks innocent and it looks simple, that's why we use it, but we have to keep in mind we are working with a much more complicated object here. And the second one is 1/2 d cube r prime v of r minus r prime psi of r prime psi of r prime psi of r. So these are daggers, and if you want you can also put heads. Or in the momentum space, this is a little bit easier to write there. So this is going to be the kinetic energy h bar squared k squared over 2m ak dagger ak, and potential scattering, let me write it like k prime u of k minus k prime ak prime ak. And
precise, there shouldn't be a dagger.
Oh yes, this one is mistake, thank you. Yes, absolutely. And last one is 1 over 2v k prime q u of q a k minus q a k plus q a k prime, if you want. So this is k prime, this is k. And typically almost all calculations and research starts with this, right? You, without saying anything, here's the model I use, you write this, and whatever you want to do, you explain. And this is always like this. Yes, VQ. So this is VQ, and these are operators. Let me k minus, k plus, k prime. And on top of that, we also need to remember, if we are working in like fixed number of particles, so-called canonical ensemble, we also write an expression for a number operator, and we already did that, d cube psi dagger of r psi of r, which is equal to k ak dagger ak. Good, so we'll be using this notation, but you'll see how we manipulate this thing. And this is how we do microscopic calculations. So we have seen all this physics, but now we are trying to get how all of these things we expected emerges from microscopic interactions and single atoms or single electrons. So first thing, okay, I have a little bit time. Let me clean up what we previously did and make it a little bit more formal. So let's think about off-diagonal long-range order. So this is off. So this is kind of like an old school terminology, but it means like a broken symmetry in modern terminology. And this O, D, L, R, O. So previously we introduced one particle density matrix. We can also do this in this. So this notation we wrote here is sometimes called second quantization. Usual quantum mechanics is first quantization. This is a terrible terminology, and I don't think anybody should bother to explain why first, why second. I think it doesn't matter. People gave bad names to all of the things, and this is one of them. And it always confuses newcomers, right? Always like, why is it second quantization? I think, and the answer is it doesn't matter. There is no first or second quantization. There's only quantization, right? And yeah. Anyways, so I want to introduce one particle density matrix in this new language. And its definition is somewhat expected. If you have R minus R prime, the density matrix is expectation value of this psi dagger of R prime, psi of R. So these are now field operators, right? And if you do the Fourier transform, this is going to be 1, okay, this is Fourier transform, 1 over V K e to the minus I K R minus R prime A K dagger A K an expectation value. And we need to calculate the expectation value in the many-body coherent state basis, right? Like, let me write that. Coherent state is going to be something like alpha in the K1, alpha in the K2, dot, 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 something like that. And if you do that, the expectation value of this thing in the coherent state turns out to be, okay, this is A, K dagger A K in that basis is going to be absolute value of A alpha alpha K squared. Then this thing becomes alpha K squared. So this is n of k, if you want, without any hat. So that's the expectation value of numbers at k. And what we expect is, like, as temperature goes to 0, what we expect is like there will be like a minimum energy configuration macroscopically occupied, and all the higher energies are like minimally occupied. What I want to say is like this nk is going to be something like a large number n0 delta of k. To keep it general, let me write it k0, but typically this k0 is zeroth momentum, right? The Bose-Einstein condensate goes and finds the zero momentum state and occupies it, and there will be like small fluctuations above this value, and typically this thing is like a smooth function. Then this one particle, I can plug this in here and look at it. So this one particle density matrix, rho of R minus R prime, becomes, so I have N0 and I have V. This is going to give me density at the condensate plus 1 over V sum over all k f of k e to the minus I k dot r minus r prime. And this n0 is n0 over volume. And if fk is smooth, right, any smooth function, if you Fourier transform, this is going to be decaying with, so this is decaying with the magnitude of r minus r prime. And what we find at the end is this expectation value, this psi dagger of r, psi of r prime, goes to a constant n0 as r minus r prime goes to infinity. Right, like this is what we previously introduced, but this is now a little bit more formal. And more importantly, right, so this r and r prime can be like arbitrarily large, right? They can be I don't know, microns, whereas like atoms are separated by angstroms or something like that. And the reasonable thing is they have to be r and r prime needs to be statistically independent. So these are different objects. Then if that is the case, I can split the thing as expectation value of psi dagger at r and expectation value of psi at r prime. Because r and r prime are very large, right? So that's like a reasonable thing to require. Therefore, this thing goes to n0, and this immediately tells me expectation value of psi dagger is non-zero. Like if you think about usual harmonic oscillator, right? Like usual Schrödinger, like undergraduate quantum mechanics, expectation values of A's and A daggers are 0 in the number basis. But now we are not working in the number basis. We are working in the coherent state basis. Even then, the variations of these number fluctuations we saw last week goes like 1 over root n. So as you reach the thermodynamic limit, these fluctuations are not important, and we can rely on coherent state to make sense of these averages. Then I want to introduce this many-body wave function, or like a superfluid order parameter, just like Ginzburg-Landau, but now we have like a microscopic principle to derive it. And this is, I'm going to put psi 0 of r without head is equal to expectation value of psi with head at r. Good. And from, in terms of this object, this one particle density matrix becomes rho 1 of r minus r prime is equal to psi 0 star of r psi 0 of r prime, and that the decaying part which we already omitted, right? And since this is like a complex, we write psi 0 of r like some norm which is going to be n0 and e to the I theta. And so this theta is going to be what we called like xy model like angle, and so this thing is norm or superfluid density. Good. And this state is macroscopically occupied at t is equal to 0. So this is psi 0 is macroscopically occupied at t is equal to 0. Good. Maybe we can take a break here, and then I can start talking about application of this in weakly interacting Bose gas in the second hour.